All right, guys. Well, this is week 5, video number 2 of general organic and biochemistry. So in the last video, we talked about naming compounds. We talked about naming ionic compounds and naming covalent compounds. And we learned how, if you were given the formula, how to write the name of the compound, and if you were given the name of the compound, how to write the formula. So that was naming ionic compounds and naming covalent compounds. Now today, the video directly after that, I want to talk a little bit about electronegativity and bond polarity. So top of page 1 of today's notes says electronegativity and bond polarity. So what determines whether a bond is ionic or covalent? Never mind how to name them, that's what we talked about in the last video, but what determines if a bond is ionic or covalent? Well, you have to consider the two atoms, or the two ions, differences in electronegativity. So what is electronegativity? Right, the definition here is the ability of an atom to attract electrons to itself. So if I think of it as like a tug of war, and I'll try to get my arms into the camera here, but if you are very electronegative, you have a very good ability to attract electrons to you. In other words, you're really good at the tug of war for the two electrons shared in a covalent bond. Okay? And I'll talk more about that as we go into further examples at the end of this video. But first, electronegativity trend. Electronegativity values, they range from 0.7 all the way up to 4.0 for fluorine. So 4.0 is very electronegative. You don't have to remember all the individual numbers, 0.7 through 4.0. Just have to know the trend. And I've drawn a little periodic table here, and you can see that electronegativity increases from bottom left to top right of the periodic table. I mentioned 4.0 is the highest. That's up there at the top right. All right. Now the noble gases are not very electronegative, but the fluorine, the halogens are. So to decide if a bond is ionic or covalent, subtract the two electronegativity values and see where you wind up, okay? So we have a periodic table here, and what we would have is we would be looking at two atoms or two ions, and we compare their electronegativity values, all right? So we have to have some sort of chart to decide whether or not we are covalent or whether or not we are ionic. So what I'm drawing here, and if you'd be patient with me, I'm trying to scratch this out for you, but I've got three blocks on top of each other. So think of this as a column, right? The very top is 100% ionic bond character. It's ionic bond all the way. The very bottom is 0% ionic character. And then I haven't drawn it to scale, but the middle would be 50%. So what I'm more interested in is the identifying left-hand column, which I haven't even labeled yet, but that's going to be electronegativity difference. So if you see my hand now, I'm beginning to label it. 3.3 is the biggest electronegativity difference I can have. That's 4.0 minus the smallest, which is 0.7. So now I'm labeling the left-hand column, the vertical line that's on the left there, is the difference in electronegativity. All right? The very bottom is the difference in electronegativity is 0. So that's like for an HH bond or a Cl-Cl bond, right? So if the difference in electronegativity goes from 0 to 0.3, well, this is a nonpolar covalent bond. If the electronegativity difference between the two atoms is 0.3 to 1.7, that's a polar covalent bond. And if it's 1.7 to 3.3, that's a big difference in the two atoms' electronegativities. So that's going to be an ionic bond. All right. So as an example, we are going to use the above chart, if you will, and mainly we'll use the left-hand vertical labeled column, 3.3, 1.7, 0.3, and 0. So order the following bonds according to polarity. We have an HH bond, OH bond, a ClH bond, an SH bond, an FH bond, and an NaCl bond. All right. So you can use your textbooks, or you could look up every atom's electronegativity in Google. Remember, you would never have to memorize this on anyone's exam, really, including my own. So, but it says here, use your textbook to look up each atom's electronegativity value, each atom's specific electronegativity value, and then you subtract and compare the electronegativity differences. Then compare it to the chart above. All right? So HH, you wouldn't even have to look up those electronegativity values. You know an H is the same as the other H. The electronegativity difference is 0. This is flat up there on that chart. It's nonpolar covalent. If you look at the OH bond, the electronegativity difference is 1.4. CLH bond, electronegativity difference is 0.9. And for the SH bond, the electronegativity difference is 0.4. For FH, 1.9, fairly high. And for NaCl, 2.1, that's the highest. Remember, we're supposed to order these guys, these bonds, these individual bonds according to polarity. So HH is on the far left at 0, working our way all the way up to HF and NAF being on the far right. Okay? Never mind why I've written the last two plus minus. We'll get to that in just a second. Basically, it's like the tug of war is so uneven that we create an ionic bond by ripping the electron away so it's no longer shared. All right, so this is the top of the next page of our notes. It says when bonds are polar, okay, that means there's an unequal distribution in each atom or each ion's ability to attract electrons to itself, right? So if it's polar, they have what's known as a dipole moment. Sometimes dipole moment is just called dipole. But a dipole moment is a direction of polarity shown by basically an arrow with a little plus, right? So it almost looks like a dagger with a little plus on the end of it. And that means the direction of polarity goes towards the arrow where the partially negative charge is. Now that little delta plus in the example for HCl, that delta plus is a partially positive charge. Delta minus, Greek symbol delta, is a partial negative charge. And it says the same thing as a dipole moment does. Partially positive on the left, partially negative on the right. Dipole moment goes towards the right, towards the Cl. Why towards Cl? Cl is more electronegative and can attract more of those two shared electrons between H and Cl. And that's why you see that cloud of electron density on the far right towards Cl. Now the next example, that one I just drew, by the way, HCl, the first example, that is an example of a covalent bond because I can still draw that dashed line. That dashed line means hydrogen is not nearly as electronegative, but he's still holding on. Now, the next example, NaCl, Na has a full plus charge, Cl full minus charge. This is an ionic bond. This is an electron transfer. The tug of war game is over for that one. All right, next topic, polarity and dipole moments. All right, so both of those that word polarity and dipole moments, that phrase, are familiar. But now we're not talking about individual bonds. We're going to talk about the entire molecule or the entire formula unit. So besides individual bonds, as we've just seen, these two ideas can also be applied to entire molecules. All right, or in the case of ionic compounds. All right, so this example is the end of today's video, and it's going to be, I believe it's A, B, C, D, and E, maybe just A, B, C, and D, but this will explain everything that we need to know for this video. All right, so the example says, for each molecule or ionic compound, indicate which ones are overall polar, not just polar bonds, overall, the whole molecule, is it polar or not? And then whether or not they have an overall dipole moment. Also, show the direction of the individual bond polarities. All right, so the first one is A, HCl. Now, HCl we've seen before. We're going to start off very slow. So H and Cl, I look up the electronegativities in this particular case. The difference is 0.9. So HCl, remember that chart I had? 0.9 fits right in there at polar covalent bond. Okay? So HCl, the H has a partial positive charge. The Cl has a partial negative charge. And I can draw my dipole moment to the right. Overall, the dipole goes to the right. Now, if you had drawn this on your paper the other way around, Cl-H, that's fine. As long as you can draw the dipole moment, it's a polar molecule. CH4, the difference between the carbon and any of the four H's is 0.4. So it's slightly polar covalent, right? It's above that 0.3 threshold on the chart at the top of the last page. So I'm drawing all these little individual dipoles, right? These little individual bond polarities, but overall, these two are going to cancel each other out, and then the top two cancel each other out. So overall, the individual bond dipoles, or the individual bond polarities, cancel each other out. So we have no net dipole moments, all right? This is an example where the molecule overall is nonpolar, but we have slightly polarized bonds 4 different occasions, all right? C, H2S. So H2S, I look up the electronegativity for hydrogen, I look up the electronegativity for sulfur, and I see that the difference is 0.4, okay? 0.4 is just like we got in the last example. This is slightly polar covalent, all right? So slightly polar covalent, I happen to draw my HSH like this, okay? And so I have a polarity, a dipole moment going down, and I have a dipole moment, in my case, going from right to left. So collectively, those two individual bond polarities, collectively, they add up for me from top right to bottom left. The fact that I can draw a dipole moment for the entire molecule means this is a polar molecule. Now, just a note there on that structure. Note, later on we will see why the following is incorrect. So if you were to draw H, S, H like in a straight line, you would suspect maybe it's nonpolar. We'll learn later on when we talk about Lewis structures and Vesper theory why that's not necessarily the case. D, NAF. Now, NAF we've seen before. Na is 0.9, F is 4.0, so the electronegativity difference is 3.1. 3.1 is way up on that chart in the ionic bond region, so that would be very polar. Na plus, that's a full plus charge. F minus is a full minus charge, because fluorine is so much more electronegative than Na that he will just rips Na's electron out, giving Na a plus charge, and now he's got Na's electron, so he has a full minus charge. Clearly, overall, this is polar. You can't be more polar than an ionic an ionic bond. This is a polar ionic compound. I could have put parentheses around the word polar and just called it ionic compounds, because ionic compounds they're more polar than polar covalent compounds. If you look at that chart, I believe it was page 2 of today's video notes. All right, so that's it for today, and I'll see you in the next time. Thanks.